Okay, so in the last video, we talked about how putting complex numbers in polar form can make multiplication with complex numbers easier. Now, we're going to do essentially the same thing but with division. We're not going to go through the derivation of this. It's kind of similar to what we did with multiplication. Instead, we're just going to jump straight to the technique for dividing two complex numbers in polar form. So if you have two complex numbers in polar form, like what we're seeing right here, and you want to divide those complex numbers, z1 divided by z2 in this case, it's the same as dividing the absolute values of those complex numbers, and then the argument of the result is going to be the difference between the arguments of z1 and z2. Remember, argument is the angle, that angle theta, or theta 1 or theta 2 in this case. So compare that with multiplication, where we multiply the absolute values and add the angles. In this case, we're dividing the absolute values and subtracting the angles. Now, I had tried to shoot this video a little while ago, and my phone messed it up somehow, so I lost the video. But I've already worked through this stuff, so that's why you're seeing this written down already. In this example, what we're doing is we're dividing z1 by z2 and leaving our answer in polar form. So the complex numbers that were given are not in polar form yet. We would have to start by converting them to polar form before doing this division. Now, you can use the conversion formulas that we did. We've already done an example of converting a complex number into polar form, but sometimes it's actually easier just to visualize in the complex plane where a complex number belongs to determine its absolute value and argument. In this case, 9i would be right here. It's a purely imaginary number, so it's on the imaginary axis. And I can see, because it's on this axis, this would be 9 units away from the number 0. In addition, because it's on the positive imaginary axis, that's going to form a 90-degree angle with the positive real axis. So the argument here would have to be 90. 9 cis 90 for z1. Again, you can use your conversion formulas to come up with that, but you would have ended up with the exact same thing. Z2, you would have also used those conversion formulas. I just kind of jumped straight to the polar form here, but I would suggest practicing this. Try converting this to polar form yourself to confirm that it's correct. We get 2 root 2 cis 45 degrees. So now that these are in polar form, what this technique that we just mentioned up here is telling us is that if we wanted to divide z1 by z2, then it's just the same thing as dividing the absolute values of z1 and z2, so 9 divided by 2 root 2, which you're seeing here, and then subtracting those arguments, 90 minus 45. After simplifying, rationalizing here, we get 9 root 2 over 4, cis of 45 degrees. That's pretty convenient. It's getting these in a polar form might take a little bit of work depending on what the numbers are, but once you have them, the division is really straightforward. Okay, so from division, we're going to move on to powers of complex numbers, or exponents. So this is the only technique that we talk about that actually has a name. It's called Dommage Theorem. I never feel like I'm pronouncing that correctly, but there it is. So what we're going to do here is talk about a technique for raising a complex number to a positive integer power, and really all it is using the multiplication technique we talked about in the previous video. So if you want to take a complex number where the polar form is given, like here, and raise it to the power of n, really that's the same thing as taking that polar form and multiplying it to itself a total of n times. That's what positive integer exponents are. It's just repeated multiplication. Now, the multiplication technique we talked about says that when you multiply two complex numbers in polar form, it's the same as multiplying their absolute values first. So if I do this a total of n times, I'm doing the absolute value of z times the absolute value of z times, a total of n times. That's the same thing as the absolute value of z to the nth power. Similarly, for the arguments, we're supposed to add those. So if I multiply these two complex numbers in polar form, I'm supposed to add theta plus theta. But if I have n of these, then that's theta plus theta plus theta, a total of n times. If you add a number to itself n times, that's the same thing as multiplying it by n. So that exponent n is actually going to multiply to our theta to give us the angle of our power here. So this is a really, really useful technique because when you raise a complex number to a power, if it's in rectangular or Cartesian form, that can be a really lengthy process if this is a large power. For example, if I wanted to do 2 plus 2i to the 4th power, that's the same thing as doing 2 plus 2i times 2 plus 2i times 2 plus 2i times 2 plus 2i, and we have to FOIL all of that. It's a big, big mess, and it only gets worse the larger that power is. But this makes short work of problems. Dommage's theorem makes short work of problems where you're raising complex numbers to positive integers. So what I'm going to do is take the 2 plus 2i that we want to raise to the 4th power and convert it into polar form, which we already did because we used that number in this example up here. Now I want to point something out. My absolute value here simplified to 2 root 2. However, 2 root 2 is the same thing as 2 to the 3/2 power. You really want to get used to working with rational exponents. If you're not all that comfortable with it right now, you'll get through trigonometry okay, but it's just crucial in calculus. We use rational exponents all the time, so this is a good place to start practicing that. But anyways, the absolute value is 2 to the 3/2 power. And what Dommage's theorem says is that we take our exponent, which is 4, and do two things with it. We raise this absolute value of z to the 4th power, so we're doing that here, 2 to the 3/2 to the 4th. And then we also take that 4 and multiply it to the argument, 4 times 45 degrees. Here is the reason why I wanted a rational exponent, because now I know from my power to a power property for exponents, it's just multiplying those two numbers. 3/2 times 4 is 6. Much, much easier than if we left that in radical form. Similarly, also we do 4 times 45 degrees, which is 180 degrees. 2 to the 6th power is 64, so in polar form, my answer is 64 cis 180 degrees. Now, there's a convention that we follow in problems like this. The original problem gave us a complex number that was in rectangular form. Unless the problem specifically says to leave your answer in polar form like this one did, the convention is to make sure your answer takes the same form as whatever you were given in the problem. So if this is in rectangular form, I want my answer to be in rectangular form, which means I need to do the extra step of converting this to rectangular form. And again, you can use the conversion formulas that we talked about previously to do that, but with an angle like 180 degrees, it's very easy to visualize that. If this is the complex plane, 180 degrees takes me to the negative real axis, and 64 units away from 0 on that part of the real axis takes me to the real number negative 64. So I can visualize that easily enough. This is the same thing as negative 64, the real number negative 64. Okay? So the last thing that we're going to do in this section is finding roots of complex numbers. Now this is a something that is difficult to imagine. You know, if I ask you, like, what is the square root of I? Well, we know what I squared is. We know that it's -1, but what would it mean to take the square root of I? Well, literally what that would mean is we're trying to find a number that can be squared so that the answer is I. And similar for any complex number. You know, down here, once we work through this derivation up here, we're going to try to find cube roots or third roots, it's the same thing, of the complex number 1 plus I, meaning we are looking for other complex numbers that can be cubed to make this 1 plus I. Dommage's theorem on the previous page kind of gives us a technique for doing this. So the idea is if we're given a complex number z, we want to be able to take an nth root. So square roots, cube roots, 4th, 5th, 6th roots, whatever. We want to be able to take the nth root of a complex number. And I'm going to say, let's let whatever that root is, let's let it equal w. It turns out that there's going to be multiple nth roots depending on this value of n. In fact, there will be n of them. So if I took both both sides of this to the power of n, this is equivalent to saying that z is equal to w to the nth power. I just want to point this out. We're doing a derivation right now. So in a problem where you're evaluating roots of a complex number, you don't go through all of this. This is just the derivation, and it'll give us a technique for evaluating roots at the end. I'm going to give a polar form to z and w. Let's let z have this polar form. Notice the argument is theta this time. And w is going to have this polar form. Its argument is alpha. Okay, so if that's the case, then, in fact, I'll even write this in here, w to the nth power, because of Dommage's theorem, is the same thing as this. We raise the absolute value to the nth power, and we multiply the argument by n. Okay, so what that means, if z is equal to w to the nth power, then first of all, the absolute values of those two complex numbers has to be the same. So that's like saying that the absolute value of z is equal to the absolute value of w raised to the nth power. Or if I take an nth root of both sides, I could say that the nth root of the absolute value of z is equal to the absolute value of w. Okay? And that's the absolute value side of things. Now I want to look at the arguments of these complex numbers. So, again, the argument of w to the nth power is n alpha, and the argument of z is theta, and those go into these cis representations, which if I expand those, it's the same thing as cosine of theta plus I sine of theta equals cosine of n alpha plus I sine of n alpha. Okay, that's the same thing as saying that, cis theta is equal to cis n alpha. Now, like I had said before, we're going to end up with multiple nth roots of a complex number. In the case of finding, the third roots of a complex number, we're going to get 3 of them. If we're going to find 10th roots of a complex number, there's going to be a total of 10 of them. But the only way to come up with all of the nth roots of a complex number is to change the way that this side looks. So I'm going to use the period of sine and cosine to rewrite this left-hand side this way. Remember, cosine of theta is equal to cosine of theta plus 2 pi k for any positive integer k. That just corresponds to, several clockwise or counterclockwise revolutions around the unit circle, giving me coterminal angles to theta. Same thing with sine. So I can change this left side into this with no problem. And the reason I'm doing that is because choosing different values of k will ultimately give me all the different roots that I need for my complex number. So if these two things are equal, then I can set the arguments equal to each other. Theta plus 2 pi k will be equal to n alpha, which I'm doing here. The goal here is to solve for alpha. I'm trying to figure out what w looks like. And alpha was the argument of w. So I would divide both sides of this equation by n in order to do that, giving me this. Alpha equals theta over n plus 2 pi k over n. Now, again, we said k can be any real number. But if you just plug in the infinity of integers in for k, you're going to find that you get a ton of coterminal angles in there, and those don't determine new roots. Those don't give you distinct roots. So we want to determine what values of k actually matter. Well, notice if we plug in n for k, then this would be 2 pi n over n, and the n's would cancel out, giving me this, theta over n plus 2 pi. Now, if I plug a 0 in for k, I just get theta over n. So theta over n is one possible value for alpha. Theta over n plus 2 pi is just coterminal to theta over n because I added a 2 pi to it. That coterminal angle represents the same complex number that theta over n by itself would. So it doesn't give us anything new if we use that. So by the time I plug in k equals n, I've started to repeat the complex numbers that I've already found, which is kind of pointless. So instead, we let k equal, and actually I'm missing a number in here, k could also equal 0. I need to make sure I include that here as well. k can be the numbers 0, 1, 2, 3, all the way up to n minus 1, whatever number comes right before n. And that gives us this expression for the full list of roots, nth roots of a complex number z. Now this, every time I've taught this course, students have there's a learning curve with this. Even if that derivation went right over your head, follow along with the next example to make sure that you're understanding the steps here. So what we're going to do is find all third roots of 1 plus I, and then we're going to plot them in the complex plane. Okay, so z equals 1 plus I. And what I want to do is convert that into polar form. Now, in polar form, this is root 2 cis 45 degrees. Okay, you can do the conversion yourself just to make sure that that's accurate, but trust me, it is. Notice alternatively, I could write that as 2 to the 1/2 power cis 45 degrees. As we saw in the previous example, those rational exponents are really nice to have. Okay, so in order to get my full list of roots for this thing, what I need to do is plug in all the values of k into this little equation right here, or this little expression. In each one of these, I'm raising the absolute value of z to the power of 1 over n, and in this case, n is 3. But what values of k will I use? Well, if n is 3, then n minus 1 would be 2. So I'm using k equals 0, k equals 1, k equals 2. I write those as 3 separate steps. So in the case of k equals 0, my nth root is going to be 2 to the 1/2 power to the 1/3 power cis of. Now, here's where the argument of the cis shows up. Theta is whatever my argument for z was. So you'll see the theta here comes from whatever your argument of z was. That means I'm looking at 45, but I'm dividing it by n. Okay, so in this case, n is 3. 45 over 3. And then if I plug a 0 in for k, this term just goes to 0 and nothing happens. So this gives me, after multiplying these exponents, 2 to the 1/6 power cis of 15 degrees. That's one of my roots for 1 plus I, my original complex number. Going on to the next root, if I do k equals 1, notice nothing changes about the magnitude of this thing. It's still going to be 2 to the 1/2 to the 1/3, which we know comes out to 2 to the 1/6. What about my argument, though? Well, I'm going to have cis of 45 over 3 plus, now this becomes, in fact, because I'm using degrees, let me make a little adjustment here. The 2 pi here is strictly for when we're dealing with radians. So the degree version of that, if we're working with degrees, would look like this. Theta over n plus 360k over n. K equals 0, 1, 2, 3, 4, all the way up to n minus 1. Okay, so the 2 pi was working with radians. We're choosing to work with degrees here, so the 2 pi becomes 360 degrees. But this becomes 360 times 1 over n, which is 3. Okay, 360 divided by 3, that would be 120 plus 15. So let's get this down here. 120 plus 15, that's 135 degrees. Okay, that's our next root. Finally, k equals 2. If I do the same thing, 45 over 3 plus, now we're plugging a 2 in for the k up here. It becomes 360 times 2 over 3, which is 2 to the 1/6 power cis of. So this is going to be 240 plus 15 would be 255. Okay? And those are the, make sure I got that right, yeah. 240 plus 15, yeah, 255 degrees. These would be the three complex numbers that we get as roots for that original complex number 1 plus I in polar form. Now we're also asked to plot them in the complex plane, and this is how we're going to wrap up this section. This reveals a really interesting pattern for those third roots of that complex number. So 15 degrees, let me say, that's right here, 15 degrees, and I'm going to say that this has a length of 2 to the 1/6 power. There's one of my roots. Whoops, there's one of my roots right there. Okay, and then if I plotted the next one, 135 degrees, whoops, I went too far. Ignore that part. That would be 2 to the 1/6 power. That's the absolute value, so that's the distance. Here we have 135 degrees, and that's where my second complex number would be. And I can tell I didn't make that the right distance, but you know, just bear with me. I'm doing this freehand. And then finally, 255 is going to be down here somewhere, or more like there. That makes an angle of 255 degrees, and again, the length is 2 to the 1/6 power. These three roots, which I did not sketch very well, form a very interesting pattern. And this is true of any nth roots of a complex number. All three of them in this case show up on a circle whose radius is equal to the absolute value of any one of the roots, 2 to the 1/6 power in this case, and they're equally spaced around that circle. My picture doesn't show it very well, but you can verify it by looking at the difference between the angles in any of these. So from 15 to 135 degrees, there's a difference of 120 degrees. That means there's 120 degrees from here to here. From 135 to 255 degrees, that's another 120 degrees. And then similarly from 255 degrees to, you know, what would be coterminal to 15, that's another 120 degrees. My picture is awful, but that can hopefully conveys this really interesting property of roots of a complex number. And this would be true even if I had done like the 10th roots of this complex number 1 plus I. I'd end up with 10 of these, all equally spaced along a circle of radius whatever I would get from finding the absolute value of this. Okay, so these problems take the longest because there's lots of roots to find in general, but I think it's one of the more interesting applications of this material. So that's it for this video, and that's also it for 10.5.